Of course, anything I can do in a loop, I can do using a forward recursion. So let me just take the loop in my code and put that in a helper function. And now we'll edit this to turn it into a recursive call. So a couple things to note. One is that I don't need these variables in my starter function because they're only used once. So I can replace them in the method call. So that's just fine. And this will work just fine, does the exact same thing. The other thing to note is that use of this dot in Java is optional. So if there's no other variable with the name that you have on the right-hand side, you can remove this dot and it works just fine. In this case, there's no variable called first, and you can see Java actually colors this blue, indicating that it is indeed a field. If you look at the constructor, you'll note that there I have a parameter that has the same name as the field. As a result, there we write this dot item gets item in the constructor. Note that in this case, this dot is necessary. If I were to remove it, I would end up doing a nonsense thing, which is just assigning a variable to itself. And in Java will give me a warning. So the this dot here is necessary because I have a local variable with the same name as the field. This is very common in constructors, and you'll see in Eclipse that the local variables are brown and the fields are blue. To convert this from a while loop to a recursive function, I'm going to remove the while, replacing it with an if, and removing the update to the iteration variable, and replace that with a recursive call. So what I'm going to do here is say something like this. Where I am moving forward each time I do the call. So we can run this and take a look at what it gives us. In this case, when we call the helper function, our helper will be called first on the first node. So note that when I invoke the helper function, I'm invoking it on the first node of the playground. That will look at the items stored there and potentially increment the result. And once we've done that, we can do a recursive call. And note the recursive call here, we end up with 2 copies of x, 2 copies of result. That's because each recursive call has its own copy of the local variables. And here, the x for the second call is the second item, whereas x for the first call is the first item. This continues out. And you'll know Graphiz gets very creative in drawing these diagrams over time. But it will eventually get to the last method, invocation, where x is not actually a pointer to an object, but instead x is null. At that point, we should have computed our result, and we can simply return the result going back. So we'll return the result here, going back through these methods. So that's a loop and a forward recursion through a linked structure. Before I show you the backward recursive version, though, let's take a step back and look at what's going on. And we'll see that we have choices with linked structures that we didn't actually have in array lists. Here's the code we had for our original loop. We can think of this computation in terms of the state of the variables as the computation proceeds. There's 2 variables in the while loop, x and result, and we can sort of keep track of what they mean at each iteration of the loop. Here I'm showing x's value symbolically, rather than showing it as, a pointer into the memory. I'm just saying, well, it's pointing to the beginning of that list. Here it's pointing at the second element, here it's pointing at the third element, etc. And you can sort of see as I compute here x is the first element, here it's going to the second element, here it's going to the third element, to the fourth element, and finally to nil, which represents the end of the list. And you can see that the result is computed as we go through the list. What's the recursive version doing? Well, it's doing the same thing, of course, but rather than thinking of this in terms of the state of the variables, we think of this in terms of the parameters and the results. So you can see the initial parameters here for each call, and then the value of the result. The initial parameter here for the first call to the helper is pointing to the beginning of the list with result initially 0. We then move on to a recursive call where we're pointing to the second element of the list and the result is initially 1. And we keep going like this all the way till we get to the bottom of the list, where eventually we hit the base case where x is null. There we simply return the result we've accumulated, which is 3. And now we just pass that result all the way back. So you can think about this computation in terms of the function call parameters and the return values. And that's different from the way we think about while loops, where we think about the state of the machine at each iteration. With recursive calls, we think about the parameters and the results. This is the same code for the recursive call, just written slightly differently here. This is a more typical of recursive code. You write the base case and return from there. Then after that, you have the inductive case. And there's something to notice here, which is that I am allowing x to be null when I call this. So if you look at the num5's function, we don't check first to see if it's null. So on the empty list, we'll just immediately call the helper function. So it is the helper function which checks x to see whether it's null or not. This is called a forward recursion with a nullable argument. So the parameter x here is nullable. It may be null. It's sometimes convenient to write code this way. It often gives you shorter code. But sometimes it's not convenient, and it's nice to check for nullity before you do a recursive call. It's important, just like it's important to be clear whether you're doing forward or backward recursion, it is important to keep clear whether or not you're working with a nullable argument or a non-nullable argument. And it's important to be consistent in how you do it. So here we're saying the pointer x may be null. Therefore, there's no reason to check it in this starter function. If I do want to check it in the starter function, I end up with subtly different code. I'm going to check if first is null, and if so, I'll return 0. Now, the nums5 function can be called, and the nums5 function may assume that its parameter is not null. What does that mean? It means here I don't have to check for nullity. In fact, I should not check for nullity because I know that x is not null. I may directly use x.item here and increment the result accordingly. But note that when I do a recursive call on x.next, I need to check that x.next is not null before I do the recursive call. And the reason here is that I am assuming that x is not null when I get to that recursive call. So if you look at the computation here, it works very, very similarly. However, in this case, I am going to stop a little bit earlier. I'll hit the base case, not when x is null, but when x.next is null. So here is going to be my base case where x.next is null. I will immediately at this point return. So you'll see this actually does one call less than the nullable version. The nullable version is going to do a call to nil, whereas the non-nullable version will not. So these are two different styles. They're both useful. In general, the nullable style will result in shorter, clearer code, and I encourage you to use it. But you should get comfortable with both of these styles. nullable and non-nullable recursion over linked structures. Returning to the version with the non-nullable argument, we'll now look at the backward variant. So of course, what we do in a backwards variant is simply invert lines 16 and 17. So we're going to swap them around to make it first do the recursive call, then after the recursive call, we'll increment the result. In this case, I am going to have to check for the non-nullity of next before I do the recursive call. And this does create a little bit of complication in the code, but it's fine. What I'm going to do here is use the conditional in the expression language of Java. So I will check to see if x is null or not. If x is null, I'll simply set the result to 0. If x is not null, then I will do the recursive call and set the result to be the result of the recursive call. You can also write this as an if then else. It works both ways. This way is slightly nicer in Java because I'm declaring the result variable exactly once. In any case, what's going to happen after I compute the result on the tail of the list will be to look at this particular element and then add it in. We can watch the code execute over here. We start at line 13 calling the helper function. The helper function starts at line 16 and immediately does a recursive call. So we will immediately do a recursive call, a recursive call, a recursive call. Once we have x.next being null, then we'll initialize the result variable to 0. We then are going to look at the item and see whether or not we have a 5. Indeed, in this case we do. We'll increment the result and then return. That return value will initialize the previous call. So we now have a result of 1 in the previous call. We check to see if there's a 5. Indeed there is. We go up to 2. And now we'll return 2 back. That gets saved in the previous call as the result variable 2. In this case, we don't have an item 5, so we'll skip and we'll simply return 2 again. That will get copied into the result variable of the previous call. And once we're there, we'll look at the x.item, which is indeed at this point 5. So we'll increment the result. And now we're done and we can return. So if you look at the computation, the way it works, we're going through the list and we're just going to stop one iteration earlier. Works just fine. So that is the backward recursion with a non-nullable argument. And again, there it is, forward, backward, forward, backward. And for those of you that don't like this query colon syntax, you can write it out with an if then else as follows. The final variation we'll look at is a backward recursion with a nullable argument. In this case, we're going to simply start our helper function immediately without checking for null. And our helper function now becomes responsible to check for null. So our helper function will check, then do a recursive call on the tail. Note that we're not checking that x.next is not null. We're not checking for nullity of x next. We don't have to. It'll be done in the subsequent call. So let's just watch this execute as well. We're going to start off here. Our first helper function will be on the first item. That's the item with 5. And now in our recursive function, we're immediately checking for nullity. We're not at null yet, so we're going to proceed and on to the next recursive call. So we'll pile up these recursive calls until we get to the end of the list. Note that the end of the list here, we're not going to stop when we get to x.next. We're going to keep going. So we do one more call on null. So the final call here will be where x is null. When we hit null for x, at that point on line 15, we can return 0. And now we're going to start doing the computation as we go back. So we'll return copying 0 into line 16 of the previous call. And then in that code at line 17, we can check x.item. And of course, now we're at the last item of the list. And so it is a 5, and we'll increment the result and return. And we're going to proceed like this over and over again. So note that the result is going to be incremented, then we return, and it gets copied. The result is copied into the result variable for the previous call. So that's where the previous call gets a result variable, and then we'll check the item and proceed. So that's how we do a backwards recursion with a nullable argument. In this lecture, we've talked about how to go through a linked list, and we've done it 5 different ways. We did it with a loop. Then we did it with a forward recursion and a nullable argument. Then we did a forward recursion and a non-nullable argument. Then we did a backward recursion with a non-nullable argument. And finally, we did a backward recursion with a nullable argument. By learning to code in all 5 styles, you'll become a much stronger programmer, in particular with respect to recursion. Common beginner errors confuse these styles. So when I'm grading exams, when I'm looking at beginner code, I often see students mixing various styles in different branches of their code. If you have a clear idea of what you're doing, I'm going backwards, I'm nullable. If you have those clear ideas, then your code will be clear as well. I've put one more slide in here for those of you that want to play around more. We've learned 2 ways to represent collections. We've done it with arrays and we've done it with linked structures. So to give you practice playing around with functions over both of these things, I've written a playground here that will create an array and a linked list for you for any given string you want to throw at it. When you create a playground here, you'll get both an array and a linked list, and you can write your function in either style and sort of play around with how they work. Next week, we're going to look at functions that change linked lists. These are much harder to understand than these simple functions which access the elements of a linked list. So you really need to get some practice playing with these accessor functions. These are simply looking at the values in the linked list and reading them. So play around with these kinds of loops, try your own functions, and next week we'll do the harder job, which is to look at how you write functions that actually change the structure of a linked list, inserting things, deleting things, reordering things. Accessing linked lists is fun, but mutating them is even more fun.